choose your favorite color. Okay, so no problem about that. So everybody fine with that? So these are the helix and this is the beta sheets. And this is the coil structures or some loops structures. Okay. So next thing, the amino acids actually. If you touch any of the portion of this structure or on the structure cursor, then it show on number actually. If you see in my case, this is ASP56 and A. It's mean ASP means is aspartic acids, one of the amino acids, and its number in this structure or residual position in this structure is 56, and it's in chain A actually, that's it. So A dot A means it's in chain A. Okay, now another thing is how to show the all the amino acid sequence. Okay, so for that you just go to favorite, then there is the option sequence. Okay, just click it. So there is a two chain in my structure, chain A and chain C, because in chain C is the ligand, although it's a amino acid ligand, that is peptide inhibitor. Okay, that's why it's so for sequence. So first you choose chain A, just click chain A and just next you click so. Okay, then it's already pop up another window, that is sequence. So this is the sequence of that MPRO or SARS-CoV-2 main protease. Okay, everybody got it? Okay, so just I cut it. Next, everybody. So next, go to favorite. Okay, then there was the option sequence. Okay, in sequence, in pop-up window there is a two options, chain A and another one is chain C, but chain C is my peptide ligand. Okay, so I ignore this chain C. I just show the sequence of MPRO. Okay, so for that just click on chain A. After that you click show. Then there is a pop-up window of main protease sequence, amino acid sequence or peptide sequence. Okay, and you also see that there's different color shaded actually. So here you can select all that structure also. Just click one of the structure or cursor. This is the sulfur, na? So just is serine. So I just cursor here. Then it shows the number here. Which number is this? So just click one of the residue or cursor on the residue. Then it's a serine 10 chain A. Okay. Similarly, this residue for glycine 174A. Okay. Similarly, every each residue we can show its residual position also. Okay, and if you select on a residue, just click, then it's already selected here also. That's this. If you zoom it by rolling the middle key of this, the selected. Okay, all this green shaded is there. It means selected that residue. Okay. So this is the sequence. And you see on a single select, then single selection, that is the select this glycine 275 residue. Just click on single residue, then it select single residue. Okay. Now find that single selection of that residue is in, yeah, that portion. You just see, this is the selection residue. Okay. So next thing is how to identify. This is in red color. So how to change this color? Okay. This select residue color. So for that you go to action. Okay. Then there was a lots of color options: ribbon, surface, color. Okay. So in color option you can change this residue, selected residue, actually selected residue color. So I just click it on blue, then it's blue. Okay, fine. Okay. Next okay. Next, there are some other options like I just close this. So there's some presets option is there. So there are some presets structural representation. First one is ribbon. That's already in my case. There's a two chain in two different color. Blue is chain one and red in red actually. Another, this is the interactive. Other option is all atom. So if you select all atom, then it show all the atom of the structure. If you see, then this yes, this is the alanine 7 residue, and this is nitrogen. Okay, and chain A. So alanine residual position is 7, chain A, and the atom name is nitrogen. Okay. Similarly, if I cursor is here, then this is GLN 127, chain A. Okay, and this is OE on atom, oxygen atom. Okay, and your cursor is like this bond position, then it's so the bonding with carbon CD. Or so this is the bonding, and this is the bond length also there. The bond 0.232 angstrom. Okay, so this is our preset second. So another preset option is the hydrophobic surface. Just click it. So it shows the surface representation of protein. Okay, where blue is the hydrophobic surface and the orange patches are hydrophilic. Okay, so this is the surface representation, and you can transparent these surface representations. From that you go to action, then there is this option surface, then the last there is the option transparency. So you just choose the transparency percentage. If I choose 80%, anybody have any question? Okay. There was a noise actually from Mihir Berak. So, sir, you have any question? Mihir Bera? Okay, fine. So this is the hydrophobic surface. Okay, so just reset it by ribbon. So this is my ribbon. Now there is a selection, so I just deselect it by clear selection. Okay, so now how to select any residue? So for that you just press curl, okay, in your laptop or in a PC, then just place curl and just click on a residue, just click and then it's selected. Okay, if you add a more selection, for that press curl plus shift. Okay, then select other residue like that. Okay, and you just adding the selection for add selection for curl and shift. Okay, but for single selection just press curl and click on that residue or the your selection in which portion you want to select, so that case. So in add case just curl plus shift and only select, just only press curl and click. Okay, so these are my selected residue in the green shaded. Okay, so the other side, and because this is the backbone. Okay, so for showing the other residue, just go action and there's option bonds, atoms and bonds, and then option is show. So if you click show, then it show other side chains of the amino acids. Okay, fine. Now I have to show the binding pocket of that inhibitor, red N3 inhibitor. Okay, so for that you just press curl and select that ligand, that is a peptide ligand. Okay, and if you select all the peptide ligand, for that you just press the up arrow, actually for your keyboard up arrow, then it's all selected, up arrow. Okay, up arrow button, just press it and it's selected whole this N3 inhibitor. Okay, so the N3 inhibitor is selected. Everybody select this N3 inhibitor. So now just show the whole structure of this N3. So for that, go to action, then there is an option show. Okay, similar case. In previous case, we select 4 residue, then show its side chain. Similarly, now we select the ligand N3 and show whole structure of that ligand. So for that, just click show. It show the ligand actually. Okay, this is the ligand. So everybody is here. Yes, okay, fine. So now I just select the binding pocket, and the binding pocket defined by the radius of 5 angstrom, as we say the center of that circle or the ligand. Ligand is the center, okay? And from the ligand we have mm, draw a circle of 5 angstrom, and all the atoms and residue within that circle are the binding pocket region, okay, or ligand binding region. So I just select the whole ligand. Now I just draw the circle. Okay, so for that there is an option. Go to select, and the option is a zone actually. Okay, just press it or click it. Then there is an option in tick uh, less than 5 angstrom from currently selected atoms. So these ligands, these are my currently selected atoms. Okay, and it's click. So I just click all the within 5 angstrom atoms. Okay, so for that you just tick here also. Select all atoms or bonds of any residue in selection zone. Okay, so just click OK, then it's selected. Okay, all the 5 within the 5 angstrom region. So all the selected residue now show its side chain. So just click so. Now see, these are the binding pocket residues. Okay, and now this is the binding pocket region residue. If you show, I just deselect it. Okay, now see the hydrogen bonds. Okay, between these residues. Okay, I just ligand with a different color. Okay, so there is a distinguish. Click color, just magenta color. So this is my ligand with different color, and other as the binding pocket residues. Okay, if you click the surface representation of that binding pocket, then click similarly John, and then select all residue. Just go to action, then there is option surface, and click show surface. Okay, this is the binding pocket, and now I just do this so the within that binding pocket ligand is there, so I just remove the surface of ligand. Okay, that magenta patches. Okay, so for that just you select chain C actually, because in chain C my ligand is there. Okay, so for that I just select chain C, and similarly go to action, then surface and height. Okay, okay, now see that there is my binding pocket. Now clear selection. Okay, so this is my binding pocket where ligand is there, and this is the residual surface. So this is the binding pocket. Everybody fine with that? I just change this background. There is option background. Okay, fine. Now see. So for this MPRO, this is the binding site. So for docking case, we know that binding site. So we choose a box in the docking actually and bind our respective ligands. So there is a process called docking process. We see from the autodock pin actually. So everybody fine with that? Okay. Okay. Now hide the surface. Okay. Now see the hydrogen bond between this peptide inhibitor and the 3CL Pro or M Pro. Then go to tools, then surface and binding analysis. Then there is option find hydrogen bond. Okay. So just click find hydrogen bond. Then this type of window is open. Then hydrogen bond color, in my case is green. You can choose your favorite color from that. Click on that box and choose your favorite color. Okay, then in my case line width is 5 and 5. You can change it by just 2, 3 or 2, 1, 2, 5. Okay, like that. You want to label with hydrogen bond with distance, then you just click this. Okay, if you don't want, then not click it. Then relax hydrogen bond constant. This is the mine 0.4 angstroms to 20 and 20 degree. Okay, there's the cutoff range of hydrogen bond mentioned in the chimera. Okay, in so this is the and color hydrogen not meeting precise criteria. Okay, so these are the criteria with color green. If you click this color, then some hydrogen bonds with not within this criteria, then it's showing this orange color. Okay, so another option is include intra-molecule hydrogen bonds, include intra-residue hydrogen bonds. So first case I choose all. Okay, so for now click apply. Now see the hydrogen bond. Okay, so total hydrogen bond. This is the hydrogen bond in this structure. Now another thing you can see, if you open this reply log, then you find how many hydrogen bond is there. So this is the 474 hydrogen bonds are found. Okay, and in the surface representation, we see that the solvent excluded surface area is 12970.5 angstrom square. Then component areas in previous case actually, and in this case the total number of hydrogen bonds is 474. Okay, now I have to choose only single hydrogen bond. Okay, so how to choose that thing? So for that you choose, I just this is the zoom in and so that this is the hydrogen bond of GLN 189. Okay, GLN 189 to ligand. Okay, this hydrogen bond. So I want to showing these hydrogen bonds. So just click on of the atom of that residue, just press curl and click on this residue. This is okay. Now open the hydrogen bond panel or hydrogen bond parameter window. Then there is an option only find hydrogen bonds. So just click it. Okay. Only find hydrogen bonds with at least on end selected. So this is my on end selected, and this is hydrogen bond. Okay. For this hydrogen bond, I just select this on end of that hydrogen bond and now apply. Okay. So now see, only this hydrogen bonds is there, other hydrogen bonds are disappear. Okay. Everybody fine? আজকে ডকিং হবে। ওকে, তাহলে শুরু করে দিচ্ছি। ওকে, ফাইন। So these are the some basics actually of Chimera. So now we move to the docking actually. So now reset all that things. Okay, and deselect all, clear the selection. Okay. So for docking, we need receptor or a ligand, and if you know the binding pocket, that's very good. But if you don't know the binding pocket, then we go to blind docking. So many server, like online server, are docking blind docking. But if you know the binding pocket of a protein or receptor, then it's better to go with directional docking. Okay, and this is a structure-based drug discovery of docking actually. Okay. And here the ligand is very flexible, or the docking in the docking, that's why very hard, because in ligand there is a lots of rotational bonds, so you don't know which rotational bonds is very stable. Okay, so that's why docking is very tough actually, although in the drug discovery we choose structure based strategy. So this is my receptor. Okay, and we know that the binding pocket is here. So this is my directional structure based docking. Okay, and today we docking this receptor with a very famous ligand or polyphenols, that is EGCG. Okay, and this is very natural polyphenols, and some recent report also says that's very, and this EGCG is very potent inhibitor against this SARS-CoV-2. So today we will see the interaction of this EGCG with this MPRO with the docking. Okay, so with first of all, you have to make sure about your system Autodoc Vina. Okay, so first you go to your C drive if you use window. Okay, local C drive, and go to program file 86. Program file 86, and there was a folder, the Scripps Research Institute. If you have installed your Autodoc Vina, then it will come. Okay, otherwise there is no any such kind of file, so make sure about that. So there is a the Script Research Institute, just click it, then there is a Vina file. Next click, then in the within this Vina file there is a three files: Vina, Vina license, and Vina split. Okay, so everybody got this thing, Vina license and Vina split. Okay, fine. Next, you have to copy these three files actually. Select and copy. Okay, and just cut it. And in the any position actually in desktop also, you create one folder, write it docking or something else, docking. Okay, and press this three file. Okay, fine. Okay. Next, go to your Chimera. Okay. Close this session. Close this session. Okay. Now, similarly, open 6LU7. This is my receptor. This is my receptor. Okay. Then go to tools. Then surface binding analysis. Then go to dock prep. Click it. Okay. Then you have a 6LU7. Okay. Delete any other things. Delete the solvent actually in crystal structure. Delete other, if any ions is there, then delete it. And any alternative positions or any methyl dump is there, then you have to remove that thing. So all that check. And the last, add hydrogen, because in the crystal structure hydrogen atoms are missing, so you have to add the hydrogens atoms. Then add charges, then write it mol to file. Okay, so just make sure about all the informations are ticked. Okay. Another thing, if any side chains are missing, then you have to click this option actually and replace using the Dunbrand 2010 Rotomar library. Okay, so it's an automated process, so don't worry about it. Okay. Okay, and this Rotomar facility is used for the side chain actually in amino acids, because in many amino acids have sometimes missing its side chain. So this library files build that side chains properly. Okay. Because in docking case, if you have any missing structures or missing side chains, then there was a missing of information, that is the interaction, some hydrophobic interaction or electrostatic or hydrogen bonds is there, na? So if any is missing is there, then the information, that interaction information is missing. That's why you have to make sure about your structure. Okay, so just click OK and write it mol to file. Okay, so just click it. Okay, the next option is hydrogen bonds. Okay, so don't about it, don't change anything because all are automated. So just make sure about your consider hydrogen bond with slower option. Okay, because this is already crystal structures, that's why there is no any static option is there, or the steric hindrance is there. If you have a model structure, then you have to make sure of steric hindrance also. But it is already crystal structure, so I just go with the hydrogen bond slower option. Okay. Another thing, the protonated states. If you have any like HIV protease like structure, then there was a aspartate acid who is in protonated states. So that protonated states effect on the binding of inhibitors. So make sure about the protonated states. So now in this case, actually the M-Pro case, there is a two protonated states are there. This is histidine actually. So we just consider the histidine amino acid. That's why the protonated states for only consider the histidine. Okay, it's automatic detect from your structure. So that histidine residue, it's calculate with protonated states with the pH value of 7.4. Okay, and that residue change its name accordingly, HIS or HID or HIE or HIP. Actually, it's automated process, so don't worry about it. And another thing is it's very easy because it's free actually, Autodoc, Vina and Chimera. So just click OK. The next is assign charges. Okay, so this is my uh, receptor. So and receptor is made of amino acids. So that's why the standard residual amber force field, this is 14 sp force field is used. So here we use the amber 14 sb force field. Okay, but although there is a lots of options, the previous force fields, that is FF03 UA, FF03R1, but FF99SB. But the latest one is FF14SB. So I just choose 14SB. Okay. And click OK. Then there is a calculate the charge actually, and we see that there is a no any net charge. And all the charge calculation are made by the anti-chamber module of Amber 18, because in this Chimera softwares, some Amber modules are within this Chimera. So don't worry about the charge calculation. It's automatic process in the software. So just it's a click based process. So don't worry with. So just okay. Now click on OK. Now click the dot prefix finish. Okay. Now see the left below. This is the dot prep finish. Now I have to save it. Okay. So this is my docking software docking file. You have create on folder. Na? This is docking folder. So this is the docking folder. I have to save it with that docking folder. Okay. Just name it receptor. Okay. This is the receptor. In automatic and save it and add it dot mol to it's automatically selected. So just click it. Okay, it's selected. So close this session, everybody. Okay, okay, so close this session. Next we go for ligand. Okay, so just go to file. No, because in the ligand case we have don't any we have no any structure. So for that we have to build a structure. So that's why you go to tools option, then there is option structure editing. Okay, structure editing, then go below, then there is a build structure option. Just click it. Okay, now see in the build structure option, there are some options: atoms, fragments, smiley, PubChem ID, peptide, helical DNA, RNA mode, RNA, like that. But in EGCG, we know the PubChem ID or smiley. So for that, you go to PubChem database. This is PubChem database, pubchem.ncbi.nlm.ni. This is the PubChem database. Okay. Write it EGCG. Okay. This is the website. I just replied on the chat box. Okay. So this is the EGCG. Write it and go to EGCG. Now see, this is the EGCG and this is the PubChem ID. Okay. This is the PubChem ID, and if you go below, then this is the canonical smiley. Okay, and if you see the option, smiley's option is there, Another option is PubChem ID. So there's a two option. If you choose canonical smile, then just go to smiley option, copy this whole things, just copy and press press it. Okay. Uh, Another option is write its CID, PubChem ID. Okay. So this is 65064. And this is residue name is I choose EGC, so EGC. This is EGC. This is three letter code, residue name always in three letter code. So that's why I choose only three letter EGC. Okay. Now go to Chimera. Now see, this is the 65064. Residue name is EGC and apply. Click on apply. Okay. The web server failed to translate smiley string to 3D structure. Now, in my case, there is a problem, so don't worry. I have already that structure, so I just open it. But you have to, in your case, please check it. If anybody get that structure, yes, got it. Okay, fine. Actually, in my case, already done, but some servers problem is there, so don't worry. I have that structure, so I just open it. Okay. In my case, this is the structure. Okay. So the same structure. Okay. But one thing, this is the structure, but this is not a minimized structures. Okay. So we have to minimize this structure. So for that, we go to tools. Similarly, the structure editing. Then there is option minimize structure. Okay. Minimize structure. So now this is the from minimization part. Here Chimera automatically choose the steepest descent step or conjugate gradients. Although you can use Newton Raphson's method also. But by default, Chimera use steepest descent and conjugate gradient steps. So I choose conjugate gradient 1000 and step size is 0.02 angstrom. Okay, fine. Now conjugate gradient I choose 500. And the interval I choose single because I have to see how the structure is minimized. Okay. Here's no any atom or I want to fix, so fixed atom is none. Okay. Now click on minimize and see this portion. Okay, how the process is going on, and side by side look into this structure, how this structure is rotate or minimize its position. Okay, so just click it. Then next hydrogen atom, because sometimes hydrogen atoms are missing, so you can just okay, click it. Okay, this is the small molecule. Okay, so I choose gas stage's charge scheme. Okay, then net charge is 0, so no problem. Now see, this is the process is going on, finishing. Steepest distance is running. Okay, 1000 process. Charge system. So my minimization process is finished. Okay. So now I have to save it by this structure with mol2. Okay. So save it by mol2 in the docking. Okay. So I just write it E G C G. Okay. And dot mol2 save. Okay. Fine. Now close this session and open the receptor mol2. This is my receptor. Okay. And this is mol2. This is my ligand. I have to dock this ligand, and this is the already crystal structure ligand. Okay. Now go to tools, then surface binding analysis. Then there is option autodock vena. You already have autodock vena option. সেখানে বসবো চার্জ করতে। Okay, now the output file destination. So for this, browse this and write it the something out. Okay, and this out file extension is for PDB-QT file because this is the charge state file of receptor and ligand. Okay, so just clear set at the output location. Okay, now fine. Now the receptor is 6LU7. Okay, and the ligand is CID 65064. Okay, fine. Next, resize search volume using button to click it, and now we choose the box. So for that, I choose any random number. That's -10, like 16, 70. This is the box coordinate, and the radius of that box is 12. I choose 12 because the ACGC size is quite large. That's why I choose size 12, 12, and 12. Okay. So now see that this is the box actually where my ligand is bound. Although if you choose, if you click any of the side of that, then you can manage it, okay, by your clicking the box portion and the position also. Okay, like that. Okay, so this is the box position. This is the binding side. Okay, okay, fine. So I just with change it by similar -10, 16, 75. Okay, so this is 60. Then it's long. Then you can change it by 70. Okay, change it by 15. You can manage this coordinate actually by putting number back to page number. So is the ligand within this box? Okay. So and that is the binding pocket. Now see, this is the box size. So change it. I choose it by 12. 12, 12. Okay. So next option is receptor option. Okay. So add hydrogen in chimera. Okay. True. Option is yes, true. Then march and remove nonpolar hydrogen. Yes, true. The march charges and remove ion pairs. Yes, because in docking, no any we have to remove the nonpolar hydrogen and any other solvent or water molecule is there, so we have to remove. So all the options you have choose true. Okay. I think in first time case, the last option, they say ignore all non-standard residues is a false, so we have to choose true actually. Then ligand option, both option should be true. Okay. So Mars charges and remove non-polar hydrogen. True. Mars charges and remove lone pair. True. Okay. The next option is advanced option. So this option tells us the number of binding modes. So it gives 10 binding modes or 10 ligand position. Okay. And the exhaustiveness research is search. Actually, it is 8 times iteration process is going on. After that, it's find the exact position of that ligand. Okay. And the maximum energy difference between two modes are 3 kilocal per mole. Okay. In your case, it's maybe 8 or 5. So you just choose it 10 actually or 5. You can choose 5 also. Then other option is executable location. So there's a two option. Opal web server. If you choose Opal web server, it takes 1 month or 15 days or 10 days because it's a server. You don't know about which job is running. 5 minutes. Okay. And then second option is local because I have already the Autodoc Vina executable file. So I just choose local. Okay. And select browse and docking. I have a docking folder and there was a file Vina executable. Okay. Just click it Vina executable. Okay. And after make sure about all the options. Okay. True, true, true. And the advanced options is 1083. Position is this -10, 14, 70, and the box size is 12, 12, 12. Hence the size position and the 36 receptor section and CID. Okay, fine. Then apply or okay. Okay. Now see in the running. Okay. In the left corner, it shows running. So wait 2 or 3 minutes. It's complete. And all the process you can see in the reply log. Okay, what's going on? This is the Amber uh, 18 softwares you use for antechamber. Okay, then for protein we use Amber FF14SB force field. Now see, we use the minimization of ligand. So these are the minimization state of ligand. Step 3, potential energy, gradient norm. Okay, step is decision minimization, step 1, then potential energy. Okay. Yes, now see the result actually. So I just close this. Now see, I have a 10 mode. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. And see the score. The first one is the score portion. This is the minus 4.2. The RMSD of lower bound is at 0, upper bound is, this is the perfect matching docking actually. And the other second, the 3 point minus 3.9, the RMSD lower bound 2.4, the upper bound is 6.5. So these are the position actually. You see. Now check the all the mode actually. So for play this movie, see the position of the different binding mode actually of that binding pocket of that GCG. And this is my crystal structure peptide. Okay, I just click it and change it different color. So it's now see, this is my old ligand and this is my new dock ligand actually. And the binding and the dock ligand also in the binding pocket. You see. Okay. Now check the and I see the binding pocket all portion. Just click it and select zone. Okay. Now select. Now check the hydrogen bond. This is the option hydrogen bond. Okay. Now see. Yes, this is the green hydrogen bond, na? Yes, this is the two hydrogen bond. I just remove the old ligand. Okay, just hide. This is the hydrogen bond. This is the hydrogen bond. You see, the This is the 3 hydrogen bond. In total hydrogen bond is 3, 2, 1. So with the receptor. So just stop this movie. Now see the fast structures, although it gets highest score, but the hydrogen bond is there is no any such kind of hydrogen bonds. Although in minus 3.9 score, there is 2 hydrogen bonds. Now see the hydrogen bonds, 2 hydrogen bond. This hydrogen bond, another one is this hydrogen bond. Okay. Similarly, to check the 3, then there is a 4 hydrogen bond. So this is the 10 mode, binding mode, but how to select which one is the best for further study or molecular dynamics simulation. Now see there is a 4 hydrogen bonds, although its score is 3. But if you see for second, this is 3.9 and there is a 2 hydrogen bond. So score is good as compared to 3, and the hydrogen bond number is reduced 2. Okay, so I think this structure is best for further study. So you have to choose like that. Choose which one is best from on the base of score and number of hydrogen bond. Okay, so this structure is base structure. So how to save this structure? So first you have to save this ligand actually. Select, then save. In the file, save PDB. Okay. And another option is action write PDB. So in the write PDB, now there's a lots of option is there, but although I just selected second option, so there is a second option is first is receptor, this ligand, and this is the dock. So there's a dock 2 ligand. So I just select dock 2 actually and just save it. Dock 2. Okay. Save. You can save this whole things by save session as docking process. Then save it. Okay. If I just cut these things and go to my docking folder, okay, then there was a py file. So just open Chimera for further actually case. Sometimes you forget all the parameters. So for that, you go to file, then open docking. This is the py. I just save doc.post.py, open it. All the things are open. Okay. Now see your all files. Okay, so don't worry about the forgot things. Like that. Okay, so that's the process of docking actually. To save, then close this session, open receptor, and similarly open the doc2. Okay, this is the doc2 file. Now save it whole things by save PDB. Okay, but before that you have to delete this ligand. So for delete, select this ligand, old ligand, then action, atoms on bond, and then option is delete. Okay, so now the structure is here, and for whole structure you have to save. Final Done. Prefix is .pdb. So you must provide a file name and the content either stack $name or $number. So just select these things and save. So like that you can save the structure. Okay, so that's the thing of docking.
Okay, so we should stop here. Okay, this is all about docking. Okay. Actually, to do it in 3 hours. Okay, but we have only 1.5 hours to finish this thing. So we had to be very hurry. Otherwise, we have taken some time to do it. Anyway, I hope at least got the base of it, how to do it. Now, of course,
sir, hello.
Yeah.
Yeah, sir. Now it's okay.
Okay.
So I think this session is concluded. So I thank the expert Professor Parimal Kaur and his team. I would like the team to introduce themselves, the research scholars to introduce themselves. They are doing a wonderful job there. So I would like them to unmute the video and audio. And just yes, sir. Sir, kindly ask your research scholars to do the same, sir.
Mohammad Khulbabu Sheikh. He's a fourth year PhD student. So today's he helped us for this docking thing. Okay, he's an expert in this molecular docking, molecular dynamics simulation, free energy calculations, and this computer-aided drug discovery. And he works on also COVID-19. Okay, so he has already published, I think, 2 papers already in COVID-19, and he's working on other manuscript also on COVID. And he's a very sincere guy.
I think I have seen. Yeah. I think I have seen him during my visit to in IIT Indore.
Yeah, you have seen him all those days.
Okay. Thank you. By name of the research scholar, sir?
Mohammad Khulbabu Sheikh. You can call him Khulbabu.
Mohammad Khulbabu said, thank you. Khulbabu, thank you, Khulbabu. And I just, sir, any other scholar who is accompanying you, sir?
No. Only I asked. Okay. This is because primarily he's working on COVID, so I asked him to go the example from COVID because only he's working on. Okay, so I got one message from Urmila Raghuvanshi. Well, I mean, I am not recording any session, so maybe Dr. Vanov can share the videos, entire videos with you all the participants.
The videos will be shared with you as well as it will be uploaded finally by the AICT Atal. So the link will also be provided to you. So I open this session for the participants to ask any questions if there are. So I'll give, sir, you can take up questions. Participants, it's for you.
Urmila, you can send me an email, okay, regarding that for this training and other things, okay?
Okay, sir, sure. Thank you.
Yeah, any other questions from the participant?
So today, I just want to tell you one thing that you have, you know that we have chosen the option here, Rotamal library. And yesterday I told you that taking consideration of the flexibility of protein is a very difficult task. And generally, we only do the side chain flexibility, and that too via this Rotamal library. Okay, we don't consider the full flexibility of the proteins, mainly the backbone as well as the large scale conformational changes that we don't take into account in modeling. So that's why in the next lecture we'll talk about, okay, now you have done the docking, now what next? Because I tell you that docking is not the ultimate thing, it is just a starting thing. It helps you to reduce the number, like from, as I said, from millions of compounds to maybe 100 compounds or 20 compounds. Okay, now from this 20 compounds you want to reduce the number further. You got a ranking of these 20 molecules. Okay, that is fine, but this ranking is not absolutely correct. So for that one we have to use better method. Okay, so we'll talk about it next lecture. Okay, what are the different methods we use, why MD simulation is needed, okay, and what are other enhanced sampling techniques that we use to get correct ranking of all the ligands so that we can identify top 5 molecules for the experimental study. Okay, so in MD simulation all flexibility will be taken into account, and many of the things that you get, I mean this value, the binding affinity value that you get actually is not absolutely correct. Okay, because these are the binding pose that you are getting is like semi-static kind of thing, not exactly you are taking into account the dynamic part. Okay, so we want to take into that via molecular dynamics. So things that you should always remember that over the time, the concept that structure determines the function has changed. Now it is the dynamic structure function relationship. Okay, and that dynamic part you always take into account via molecular dynamic simulations. Okay, so if you have any other question, just ask me. Okay, otherwise we'll continue to talk in the, I think tomorrow we'll talk about it further.
Yes, sir. Yes, sir. One more question is there, sir. What is the percentage accuracy of MDC by
What is MDS?
MDS?
Molecular dynamic simulation. No, molecular dynamic simulation is just one of the technique to run to get the dynamic part. Now, what are the methods that, I mean, the analysis tool that you are using to calculate the binding affinity? That is important. So, for example, if you use free energy perturbation or thermodynamic integration, that is very, very correct. The error level is 0.2 to 0.3 kcal per mole. Okay. Now, if you use molecular mechanics, Poisson's-Boltzmann surface area, then the error is from 0.8 to 1 kcal per mole. But thermodynamic integration or free energy perturbation is very costly. Okay, costly in the sense of computational resources that you require. But if you have very small set of ligands, then of course you can utilize this scheme. That is the best method. Well, I mean, water is very important, as I said. I mean, see, you must have noticed one thing that in one case you got 4 hydrogen bonding. Okay, but you saw that the total binding affinity is less than the case where only 2 hydrogen bonds are formed. Why? Because if you kick out the water molecules, okay, then the penalty arises due to the dissolution of polar groups. So water plays a role, of course, there. Okay, and the dissolution of polar groups, that is always a penalty. That means that always disfavors. So that's why, although you have formed 4 hydrogen bond, thinking that that will be the best pose, but that's not the best pose, because the penalty is so high. Whatever the electrostatic gain that you are getting via hydrogen bonding is completely overcompensated by this unfavorable contribution from dissolution. Okay, that's one aspect. Now, sometimes I told you that if your binding cavity is hydrophilic in nature, often it is possible that there could be a water molecules inside, because since it is hydrophilic, the amino acids love to interact with the water molecules. Now you have a ligand. How would it interact with water molecule then? So first it forms a hydrogen bond with water molecules, and the water molecule then again forms a hydrogen bond with ligand. Okay, so this water molecule plays a bridging hydrogen bond actually. So that is also very important. So that way you are taking into account the hydrophilicity of your binding pocket, as well as the hydrogen bond formation also. Okay, so you are also minimizing the dissolution of polar groups that way.
Yeah, sir.
Generally, okay. Just Urmila's one question: water should be kept during the docking? No, generally we don't keep the water molecule during the docking. So that's why I said that. So post docking, you should do the MD simulations. Now, when you do MD simulation, you simulate it in a solvent box. So water molecules are there. So if it is a hydrophilic surface, so of course water molecule will move into that cavity. Okay, because water molecules are continuously moving around in the box, so it will of course go there and bind. So, but for docking, we don't use it. Docking, we treat the water molecules, or rather the whole solvent, in an implicit way. Okay, so generally water has a dielectric constant of 80. So we said that, okay, instead of using the atomistic water molecules, why don't you treat that this protein and the ligand is kept in a infinite dielectric medium, which is characterized by epsilon is equal to 80, because that is the dielectric constant of water. So that way you can take into account. But what is missing then? Well, you are missing the hydrogen bond. If any hydrogen bond is formed between the amino acid and the water molecules, because there is no atomistic water molecules, there is only dielectric constant. Okay, so that way you are missing, but you are taking into the overall solvation part in an implicit manner. Basically, you are minimizing the error. Of course, you are not completely addressing the problem, but to some extent, of course, you are addressing it. Okay. What happened during ligand minimization? Well, the ligand minimization means you are optimizing their orientation in the binding pocket. You are minimizing the energy. As I said that, the lower the energy, stable the position is. If you select a higher energy position, of course, during the MD simulation, it will come out. It's a bad position. There could be a clash with the other atoms. So by minimizing, you are relaxing. You are relaxing your structure. If there is any strain energy, okay, so that you are relaxing. That's what happens in the minimization process. If there is any bad contact, yesterday I told you that there could be some basically bump with the receptor, no? And I said that generally we can use softer potential to get rid of the bump. But if you don't use softer potential, during this minimization, this bump will be taken care. So those classes will be relaxed. Okay.
So, sir, we can call this session.
Yeah.
Yes, sir. So once again, I thank the expert Professor Parimalkar sir and his team member Seth. I thank you very much. Of course, this session was attended by, again chaired by two of our members, Dr. Jumrik Madam and Dr. Devjit Datta. So Devjit Datta, he has just left for an assignment. So briefly, he is also from ISI Kolkata. He is serving with us for the past 5 years. So probably he may be chairing next maybe future sessions. So I thank the chairs also. Once again, I thank all the participants. And on behalf of our institute and Atal AICTE, so thank you, experts and participants. Yes, sir. Okay, we can join tomorrow for 2 more sessions by you and your team. Thank you, sir.
Okay, thank you. Thank you all.
Yes, sir. Yes, sir. Bye. So participants kindly join at 1:40. Uh, so I will be also shortly sharing one PDB file which is going to be used in the next session. Yeah, please you look out for that. Yeah, thank you.